3 moles of an ideal monoatomic gas perform a cycle as in figure. So we have this figure, okay? So we have a graph between pressure and temperature. The gas temperature in different states are T1 equals 400 Kelvin, T2 equals 800 Kelvin, T3 equals 2400 Kelvin, and T4 equals 1200 Kelvin. Determine the work done by the gas during the cycle. So we are asked to find work done, okay, during the cycle. So we have work done, or we know work done, okay, equals pressure times volume, okay. So I'm writing work done equals P times delta V. So we have this. And in this question, okay, we are asked to find work done during the cycle 1, 2, 3, 4, 1, okay. So we are asked to find this. Clear? Now, from question, okay, we have state 1, 2, 3, and 4, and the temperature, okay, of state 1 is 400 Kelvin, and temperature of state 2, okay, it is 800 Kelvin, and temperature of state 3 is 2400 Kelvin, okay. It is 2400 Kelvin, and temperature of state 4 is 1200 Kelvin, okay. So we have this. So we can divide this cycle, okay, that is cycle 1, 2, 3, 4, 1, okay. So I'm writing in this way. We can divide cycle 1, 2, 3, 4, 1, okay, into different segments. So we have segment, okay, 1, 2. So we are writing 1 dash 2, okay. Next we have segment 2, 3. We have segment, okay, 3, 4. And finally we have segment 4, 1, okay. So the direction is given in the figure, okay. So we are moving from 1 to 2 in this direction, from 2 to 3, from 3 to 4, and 4 to 1. So we have this. Now we can see we have 3 moles of an ideal monoatomic gas, okay. So I'm writing number of moles, okay. This is given in the question. This is 3. So we have this. Clear? Now, what we do is that, okay, we take, okay, or let us take this for segment, okay, 1, 2, and 3, 4, okay. So we have this. Let's look into this figure, okay, or let's understand with reference to this diagram also, okay. So I'm redrawing this diagram. So we have segment 1, 2, okay. So this is a straight line, and next we have segment 3, 4. So we have this. So what we find for segment 1, 2, and 3, 4, okay, we find pressure is directly proportional to temperature. So we find this. And from, okay, we have, okay, pressure directly proportional to temperature, okay, for constant volume. So we have this. Clear? So this is from Charles' law, okay? It is from Charles' law. So we have this. Therefore, for segment 1, 2 and 3, 4, okay, volume is constant. So what we find, volume is constant. There is no change in volume. Okay? So we find this. Therefore, from this equation, okay, work done, okay, work done by gas, okay, for segment 1, 2 and 3, 4 is 0. So I can write in this way, 1, 2. So this is 0. Okay. And work done in segment 3, 4 is also 0. Why? Because pressure is directly proportional to temperature for segment 1 and 2 and segment 3 and 4. It means that the volume is constant for segment 1, 2 and 3, 4, due to which work done by the gas in the segment 1, 2 and 3, 4 is 0. So we need to note this, okay? So we have this. Case 2, okay? For segment 2, 3. And we can see in this figure, okay? For segment 2, 3, pressure is constant. Okay? And if pressure is constant, then we have, okay, isobaric. So we have isobaric. Case 2. Case 2. For segment 2, 3, okay? We can see in this figure, okay? For segment 2, 3, pressure is constant. So I'm writing in this way, okay? 2, 3, pressure is constant. So if pressure is constant, then we have isobaric, okay, process. So for segment 2, 3, okay, the process is isobaric. So we need to understand this, okay. Now, work done in this segment, okay, 2, 3 equals Now let us mark this, okay? We can see pressure is constant for segment 2, 3. And for this segment, okay, 4, 1, pressure is constant. So work done, W23, okay, equals pressure, and pressure is P2 times change in volume. So let V2 be the volume, okay, for state 2, and V3 be the volume for state 3, okay. So we have this. So this equals P2 times V3 minus V2. So work done for the segment 2, 3, okay, equals P2 V3 minus P2 V2. So we have this. Okay. Now for segment 4, 1, okay, or segment 4, 1, we find pressure is constant, okay. For this segment, we find pressure is constant. So the process is isobaric, okay, for the segment 4, 1, and work done, W41 for the segment equals pressure. So the pressure corresponding to segment 4, 1 is P1, and P1 is constant, times change in volume. So we can write P1 times, so we have V1 minus V4, okay. So we have this. So W41 equals P1 V1 minus P1 V4. So we have this. Now total work done, okay. Total work done during the whole cycle is W1, 2, 3, 4, 1. So that is, we can write in this way, okay. W1, 2, 3, 4, 1 equals work done W12, okay, work done, and work done for the segment, okay, or work done on the segment W23 plus work done on the segment 3, 4 plus work done on the segment 4, 1. So we have this. As I said earlier, total work done equals work done on the segment 1, 2, 2, 3, 3, 4, and 4, 1. So we have this. Now we know, okay, work done on segment 1, 2, okay. So this is 0, and work done on the segment 3, 4 is 0. So we have this. Clear? Therefore, we can write total work done equals work done W23 plus work done 4, 1. So we have this. Clear? And we are going to put these two values in this equation. Therefore, we can write, okay, total work done equals W23 equals P2 V3 minus P2 V2 plus, and W41 is P1 V1 minus P1 V4. So we have this. Clear? We have this. Total work done during the whole cycle, okay, equals P2 V3 minus P2 V2, okay, P2 V3 minus P2 V2 plus P1 B1 minus P1 B4, P1 B1 minus P1 B4. So we have this, and let us call this as equation 1. Okay, we have this. Now, from ideal gas equation, okay, so we are going to use ideal gas equation. Ideal gas equation, okay, we have PV equals nRT, and from quotient, okay, n equals 3. So we have this. So we are going to use ideal gas equation for state 1, okay, state 2, state 3, and state 4. And the volume at state 1 is V1, volume at state 2 is V2, volume at state 3 is V3, and volume at state 4 is V4. So we are going to use ideal gas equation, okay. So I'm writing in this way, using, okay, ideal gas equation. Let us write in this way, using ideal gas equation, PV equals nRT at state 1, 2, 3, and 4, okay, and we have n equals 3. So for state 1, we have P1, V1 equals n is 3, R T1, okay, the temperature is T1. So we have this. Clear? And for state 2, we have P2, V2 equals 3 times RT2. So we have this. And for state 3, okay, the pressure is P2. So P2, V3 equals 3 times RT3. Okay, so we have this. And for state 4, the pressure is P1. Okay, so we have P1, V4 equals 3 times RT4. So let us call these equations collectively as equation 2. So we have this, okay. Now, from 1 and 2, okay, total work done equals P2V3, and P2V3 is 3 times RT3 minus P2V2, and P2V2 is 3 times RT2 plus P1V1. So P1V1 is 3 times RT1 minus P1 V4, and P1 V4 is 3 times RT4. So we have total work done equals 3R. Okay, so I'm taking 3R common, and we have T1 minus T2 plus T3 minus T4. So we have this equation. Okay, let us call it equation 4, and we know R equals 8.314 joule per mole per Kelvin, and it is called the universal gas constant. Okay, so this is universal gas constant. Now, total work done during the whole cycle equals 3 times 8.314, and T1 is 400 Kelvin. Okay, so we have 400 minus T2 is 800 Kelvin plus T3 is 2400 Kelvin minus T4 is 1200 Kelvin. So let us find this. Okay, so we get 800, okay, times 8.314 times 3. So let's find this. So total work done during whole cycle is 199, okay, 53.6 joule. So we have this. Clear?